Greetings and salutations, magical chemists. Today we're going to talk about the difference between intramolecular forces and intermolecular forces. Intramolecular forces are more commonly known as chemical bonds. So ionic bonds, covalent bonds, and metallic bonds are all examples of intramolecular forces. Intermolecular forces, or IMFs, is the attraction between two or more distinct molecules or particles. In a physical change, only intermolecular forces are broken because no chemical bonds are being broken. But in a chemical change, since chemical bonds are being broken, intramolecular forces are broken. Chemical bonds, or intramolecular forces, are always going to be much stronger than intermolecular forces. I have a gruesome but hopefully helpful analogy for you. Think of children getting ready to play that game, Red Rover, where everyone holds hands and someone else tries to break through the chain. Well, when the children are holding hands and someone runs into them, trying to get them to be able to break through, their hands that are being held together, these are the attractive forces between the children. So these would be the equivalent of IMFs in our analogy. However, the bonds within the children, like the tendons and muscles and bones that are holding the body together, those are the chemical bonds. And so hopefully, I truly hope that this is how the game is played, if someone runs and tries to break through the chain of children, their hands will separate. The intermolecular forces will be overcome, but they're not going to lose an arm at their shoulder. I hope not. I really hope not. That's the chemical bond. It takes a lot more force to rip someone's arm off their shoulder than it does to just get them to stop holding hands. So there you go. An absolutely horrible way to make sure you remember that chemical bonds are stronger than IMFs, always. Let's take a look at the three main types of intermolecular attractive forces between separate particles. The first one is called London dispersion forces, or sometimes more commonly just dispersion forces, or LDFs. Mastering Chem will call these van der Waals forces, although I would claim that's not 100% accurate. However, that is what they're referring to. So London dispersion forces, or LDFs, happen between all molecules and atoms. Polar, nonpolar, doesn't matter. LDFs occur because of what's known as an instantaneous or temporary dipole. It creates a momentary attraction between two neighboring particles. And what's interesting about this is they actually can be a very strong attractive force. So even though LDFs are often known as the weakest of the IMFs when they're compared, actually, if you have a very large particle with lots and lots of electrons, you can have very strong dispersion forces. Dipole to dipole attractive forces are, well, pretty much what they sound like. It's the force of attraction between two opposite dipoles on separate molecules. Now, this occurs between polar molecules, things that already have a permanent dipole moment, not just a temporary one, like in London dispersion forces. Notice how the partial negative on the dipole of one particle is attracted to the partial positive on the dipole of another particle. Coulomb's law back again. Also note, we represent these intermolecular forces as a dotted or dashed line. It's not a solid line because it's not a chemical bond, it's just this attractive force. Okay, one more IMF. These are known as hydrogen bonds, or hydrogen bonding attractive forces. And I personally think this is the most poorly named thing in chemistry, because technically hydrogen bonding is not a chemical bond. What? Nope, it's just an IMF. It actually gets pretty dang close to a chemical bond, which is where the name comes from. It's very strong. It's basically a super strong dipole to dipole attractive force. But a hydrogen bond, that attraction is not a covalent bond, despite the name. Okay, I kind of just highlighted that picture to death, but it's because the difference between covalent bonds within a covalent particle and hydrogen bonds between separate covalent molecules is so easily misunderstood. I mean, they're terribly named, but this is something that is highly AP tested, and you have to understand the distinction. Now, you might be thinking, okay, but this hydrogen bond, why is it such a strong dipole to dipole attractive force? Well, we like to say that hydrogen bonding is so much fun. Nope, not fun, fun. And that's because hydrogen bonding occurs when you have a molecule where a hydrogen is covalently bonded to a fluorine, oxygen, or nitrogen, which creates this really strong partial positive, partial negative. And then the attraction between that super positive hydrogen and the lone pair on a fluorine, oxygen, or nitrogen of another molecule. So hydrogen bonds, I know, I say this a lot, but hydrogen bonds are not chemical bonds. Okay, important note to make. If you are comparing particles of a similar size, means they have about the same number of electrons, well, hydrogen bonding IMFs will be the strongest IMF by far. Then will come dipole to dipole IMFs, and lastly, and most weakly, are London dispersion forces. But this is only when you are comparing things of similar size. Now this line down below is very confusing. This was not supposed to be on this page. Meep, 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 meep. That is supposed to be the title on the top of the next page. So let's take a look. There are two more IMFs that are tested. These are only things that could happen when you have one type of particle mixed with and attracted to a different type of particle. For instance, you could mix things that are polar and nonpolar together. It won't work very well, but it's totally a thing that could happen. So if you have something polar, that means it has a permanent dipole. Well, if that's sitting next to something that is nonpolar, nonpolar things, of course, don't have a permanent dipole, so it's neutral. Very fun. However, just the fact that you're sitting next to a permanent dipole creates what we call an induced dipole, a temporary little dipole in your neutral molecule. Because if you have a partial positive, the electrons in that neutral molecule will be attracted to it, making that one side partially negative and the other side partially positive. So it is induced by the presence of the permanent dipole. So these are literally known as dipole-induced dipole attractive forces. So this is an answer that you will only want to put if you are talking specifically about attractive forces between two different chemicals, one polar, one nonpolar. Similarly, but more strongly, what is actually even stronger than hydrogen bonding attractive forces, ion dipole attractive forces. This is what happens when you dissolve salt into water. Well, ionic compounds, if they are soluble, will ionize into charged particles. And as you can imagine, if you have a full partial charge, that's going to be super attracted to that permanent dipole, that negative, partial negative. So this attractive force is actually very strong, even stronger than hydrogen bonding, and it's because you've got a full charge on the ionic compound. So this is officially the strongest IMF, but it only occurs if you dissolve something ionic into something polar. So to put it all together, and with the note, you're comparing things of similar size, ion dipole is by far the strongest, then hydrogen bonding, then dipole to dipole, then dipole-induced dipole, and then LDFs. Okay, let's summarize this in one giant table. It'll be lots of fun. So one of the things that is absolutely essential to success in describing intermolecular forces is being able to take a look at a given substance and determine what IMFs are present between particles of that substance and what is the dominant or strongest attractive force. Well, if you have two nonpolar things, either the same nonpolar substance or two different nonpolar things, or just single atoms all by themselves, the only attractive force you have is London dispersion forces, which means, of course, dispersion forces will be the strongest attractive force they have. If you look at polar and nonpolar combined, well, dipole-induced dipole is going to be dominant. If you look at things that are polar but not having any fun, then it would be the dipole to dipole attractive forces. And if they're polar, but they are having fun, then it would be the hydrogen bonding attractive forces. And if you take something polar and add in ions, you will get dipole to dipole attractive forces. So you'll notice there's a clear pattern in what is the dominant or strongest IMF in a particular substance. Now, technically speaking, every solution has, of course, whatever their dominant IMF is, but they also exhibit all the weaker IMFs as well. So technically, if you have a solution of polar and nonpolar things, not only do they have dipole-induced dipole, they also have London dispersion forces. Things that are polar and not having fun, well, of course they have dipole to dipole, the strongest IMF, but they also have dipole-induced dipole, and they also have, London dispersion forces. So you can basically fill in all the rest of this because they've got anything weaker than their most dominant IMF, almost always. They will have all of them. But there's something sneaky here that I want to point out, especially when answering free response problems. You might have noticed that I put the example solutions that are mixtures of two different substances in italics. And I also did the same for the IMFs that occur between these multiple compounds. That's because even though it's true, if you have dipole to dipole attractive forces, you also have dipole-induced dipole. Nobody talks about that. So you actually are only expected to give the answers of these things, and basically the italics ones, these answers are only ever given when you have a solution of the particular thing where that is the dominant force. Well, ion to dipole only shows up if there's ions and dipoles, but nobody ever says, oh yeah, well, water has dipole-induced dipole attractive forces. It does, but we don't talk about it. It's weird. It's like it's Bruno or something. So please make a note that even though, yes, dipole-induced dipole is a thing, you're still not going to list it as an answer if you were trying to say what are all the IMFs exhibited by a compound. So if you were asked to basically, what are all the IMFs that nonpolar things have? Well, easy, right? Dispersion forces only. If you were asked for all of the IMFs that something that is polar but not having fun has, you would be like, well, it's dipole to dipole and London dispersion forces. If it was polar and having fun, well, of course, you talk about hydrogen bonding and dipole to dipole and dispersion forces. And if it is the polar stuff mixed with ions, then again, you would list all of these things, but for some reason, not dipole-induced dipole. Okay, I hope that's not too confusing. Let's find out. Let's go ahead and practice. Okay, in the chart below, you are given either one molecule or a pair of things. And what you're going to do is label each given substance as polar, nonpolar, or an ion. And you're going to determine if it's polar, is it having fun? And then you're going to use that information to determine what IMFs are present. Let's go ahead and try one together. All right, CH3, CH2, CH3. Hydrocarbon, right? Carbons, hydrogens, that's all we got. You absolutely have to know this is nonpolar all the way. Well, the second box says what IMFs are present and underline the dominant IMF exhibited. Well, it's nonpolar. Same answer for each. All they have are London dispersion forces, so those are definitely the strongest IMFs. Let's try one more together, and then you can practice. All right, HF. Well, if you're taking a look at this, hopefully you would realize that hydrogen and fluorine are very, very different in electronegativity, which makes this an extraordinarily polar bond. And it's not just polar, it's having fun. Well, there's the F, right? So if it's a hydrogen covalently bonded to a fluorine, oxygen, or nitrogen, we consider it having fun and capable of hydrogen bonding. By the way, please do not use the fun as a free response explanation. It is a great trick to remember which things have to be chemically bonded to hydrogen to have things with hydrogen bonding. But if you start explaining, well, it's totally having fun, and no one's gonna really know what you're saying. So remember, quick memory trick, not an explanation. But now, hopefully you realize, since it is a polar molecule having fun, it has 3 different IMFs present within that solution. Hydrogen bonding attractive forces, dipole to dipole attractive forces, and London dispersion forces. But since it has all 3, the dominant or strongest IMF is definitely the hydrogen bonds. Okay, both of those examples were looking at IMFs within a substance with only one thing. Let's go ahead and look at a mixture and determine IMFs. I'm going to go ahead and bypass a couple of examples because I want to look at guanine and cytosine, 2 DNA nucleotides. Hopefully remember that guanine and cytosine are a match, they're a pair. Well, let's see if intermolecular forces can explain why. Okay, the one thing on this thing that annoys me is that it does not show the lone pairs, so I'm going to add those. It can be harder to determine if a giant molecule is polar or nonpolar. DNA is a giant molecule. But what you're looking for are these regions of asymmetrical electron density. And hopefully you can recognize, oh look, nitrogen bonded to hydrogen. Oh my goodness, it's having fun. That is automatically going to be a super strong dipole. These are both polar. And they have a hydrogen directly bonded to nitrogen. That means they're totally having fun. One of the things that I find fascinating about hydrogen bonding is that although you, of course, totally need that covalent bond between nitrogen and hydrogen to create the extreme dipole, technically you might be looking at this going, but there's no hydrogen on that one. And that's okay. You actually can have a hydrogen bond attractive force between the hydrogen on one molecule that's covalently bonded and a lone pair on the nitrogen of another molecule. So that's why, same thing over here. You have these attractive forces between the hydrogen and the oxygen, even though this oxygen doesn't have any hydrogen of its own. And then up here, same thing again. Oops, wrong color. So there are actually 3 different places where guanine and cytosine match together, basically are stuck together with these very strong sticky IMFs. And that's what holds the 2 strands of DNA together. It's really cool. So now, of course, we have to figure out, well, what kind of, intermolecular attractive forces are there? Clearly, hydrogen bonds. I can't stop talking about them. But I would like you to take a moment and see what you think. Write down, remember, every single IMF that might be present that you would answer for a free response. And when you're done, we'll go ahead and check. So pause the video now. All right, are you ready to check your answers? Let's try it. So between the 2 strands of DNA, we have hydrogen bonding, dipole to dipole attractive forces, and London dispersion forces, but those hydrogen bonds are the dominant attractive force. All right, now would be a great time to pause and try some of the other practice problems on your own. I'm going to move forward to one last thing before ending this video. Answering free response questions about intermolecular forces can be tricky. And turns out, IMF-based free response questions are very popular on the AP test. So clarity of language is essential. So there are many times where a student who has written a mostly correct answer loses a point because they're talking about like a state change or a physical change, and they talk about how the, chemical bonds are being broken during a state change. And that is absolutely not. A state change is, change in state of matter. The whole point is you're not breaking chemical bonds. Another one that's a little sneakier is saying that molecules are being broken apart. Well, what's kind of misleading about this is you're like, well, if I'm overcoming the IMFs, you're basically separating 2 separate particles. When you use the phrase broken apart, you cannot tell if you are trying to describe separating 2 different molecules or literally breaking apart a molecule into its component atoms. And because you can't tell, I can't give you credit for that answer. So don't say that either. So there's a distinction you'll notice. It's not 100% true, but I tend to use this because it helps my brain differentiate. When I'm talking about chemical bonds, intramolecular forces, we talk about those being broken, right? You break chemical bonds within a compound. And chemical bonds are within a single molecule. For intermolecular forces, I will commonly use a slightly different language just to differentiate. Instead of saying breaking IMFs, I like to say you are overcoming IMFs. Instead of saying break apart molecules, just say separate molecules. That's because IMFs are between separate molecules. Okay, let's go ahead and try just a teensy bit of free response practice. So in this free response practice, you have two separate equations, and they're asking you, it's kind of two questions. What type of intermolecular or intramolecular attractive forces must be overcome for each process to occur? So I think this would be a great one for you to attempt. So go ahead and decide, what is it first? Are you overcoming inter or intramolecular attractive forces? And then what type of them? And when you're ready to check, unpause the video. First, it's important to recognize the first reaction shows a chemical change, and the second one is showing a state change. So that helps you identify if it's inter or intra forces being broken. Okay, a chemical change, of course, is breaking bonds, intramolecular forces. A state change is just overcoming intermolecular attractive forces. But we also need to identify in this question, there's one last thing. They want to know what type of said force is being overcome. Well, for a chemical reaction, they're asking you what kind of bond you're breaking. And these ones in carbon dioxide, of course, would be covalent. For a carbon dioxide state change, well, it's nonpolar, so only LDFs are being overcome. You might be thinking, wait, I know we're breaking bonds in the first one, but aren't we also overcoming IMFs? Well, I mean, yeah, you are, but remember the children. The IMFs are negligible, so they would not be considered a correct answer to this problem. And there you have it. That would be a classic free response problem that makes sure that you understand the distinction between intra and intermolecular forces. So thank you for playing with the glories of chemistry.